नमस्ते सर।
Good afternoon, sir.
गुड आफ्टरनून। नमस्ते सर।
सर गुड आफ्टरनून सर।
गुड आफ्टरनून।
सर का मैसेज आ गया, वो 2-3 मिनट में ज्वाइन कर रहे हैं सर।
हाँ हाँ ठीक है। सर नमस्ते। अग्रवाल सर, आवाज आ रही है सर?
हाँ आ रही है। नमस्ते।
अच्छा अच्छा।
नमस्कार सर।
ठीक है सर।
अब तो कंप्यूटर पे एक दूसरे को देख रहे हैं अब तो।
जी जी अब यही हो गया है।
हाँ। शाम भी तुम तो आती ही नहीं, कि हम तो एक आध बार डिपार्टमेंट गए, तुम मिली नहीं।
नहीं सर,
नहीं।
आजकल वीसी साहब बहुत मीटिंग कर रहे हैं सेनेटियल, उसमें रहते ही। अभी तो मैं डिपार्टमेंट में ही बैठा हूँ। ठीक है, कहते हैं
नहीं, हम शाम्भी से कह रहे थे, शाम्भी।
नहीं नहीं सर,
नहीं,
आते
शाम
हैं
में भी
हम भी।
आती रहती है।
हम्म।
एक्चुअली अब ये हो गया है,
तुम अपना
थ्योरी
टाइम
क्लासेस
बता दो,
ऑनलाइन
टाइम हम
लिया
आ
जा
जाए।
रहा है और प्रैक्टिकल क्लासेस हम लोग कभी
प्रैक्टिकल क्लासेस
फिजिकल
तो
कभी उससे करा
फिजिकल
रहे
शुरू
हैं।
कर दिए हैं।
यस सर। सर प्रैक्टिकल अब होंगी, अभी शुरू नहीं हुई है सर, लेकिन ऑफलाइन प्रैक्टिकल क्लासेस शुरू हो
अशोक आरके सिंह सर भी क्या ज्वाइन किए हुए हैं?
सर हाँ सर ने ज्वाइन किया हुआ था सर, मैं देख रहा
अच्छा
था।
अच्छा अच्छा। सर से हमने रिक्वेस्ट करी थी कि
सर है, आर के सिंह सर है सर हमारे साथ।
अच्छा अच्छा। हाँ वो
सर
उनसे
वो
मैंने
वॉइस
कहा
नहीं
था।
है, वॉइस से कनेक्ट नहीं है सर वो।
सर मुझे
अच्छा,
लग रहा है उन्होंने डेस्कटॉप से शायद ज्वाइन किया होगा।
हो सकता हो।
माइक नहीं बंद करा रहा है सर का।
सर को थोड़ा ज्वाइन करने में दिक्कत होती है, आरके सिंह।
वैसे तो मोबाइल से भी ज्वाइन कर सकते हैं ना।
जी जी
हाँ सर,
हाँ,
बिल्कुल
मोबाइल
कर
से बड़े
सकते
आराम से ज्वाइन कर सकते हैं।
क्या ये यूट्यूब पे भी दिखाया जा रहा है?
जी
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 सर।
हाँ, यूट्यूब में डायरेक्ट स्ट्रीमिंग करा दी है।
हाँ सर, नमस्ते सर।
नमस्ते।
और सर क्या हाल है सर?
ठीक है, तुम दिखाई नहीं दे रहे हो।
हैं?
दिखाई नहीं दे रहे
शकल
हो।
दिखा दो राजीव सक्सेना सर।
अच्छा सर, कैमरा ऑन करना पड़ेगा सर।
तो कैमरा हमारा तो ऑन है।
अरे आपका ऑन है, मैं भी ऑन करता हूँ।
हाँ सर कह रहे हैं शकल दिखा दो यार।
दिखा रहे हैं, दिखा रहे हैं, दिखा रहे हैं, दिखा रहे हैं, दिखा रहे हैं। हाँ। दिखी सर शक्ल?
हाँ।
हमने कहा सर शक्ल देख। कितने 3 बजे आएंगे सर?
आने वाले हैं, अशोक जी
आने
बता
वाले
रहे थे
हैं।
अभी।
सर हाँ, सर का
हाँ
मैसेज आया था अभी 5 मिनट पहले, कह रहे कि बस 5 मिनट में ज्वाइन कर रहा हूँ।
हाँ हाँ ठीक ठीक।
चलिए, उनको उनको बुलाया जाए। ठीक सर।
हेलो सर, जस्ट मिनट। सर ने ज्वाइन कर लिया सर, एक बार उनको अनम्यूट कर दीजिए सर।
हैं? हेलो।
हेलो।
थैंक्स।
ओके सर।
अभी
नमस्कार
सुनाई
सर।
दे रहा है?
यस सर, यस सर।
यस सर,
यस सर,
सुनाई दे रहा है
नमस्कार
बिल्कुल।
सर।
थैंक यू सो
सर
मच सर फॉर
नमस्कार।
ज्वाइनिंग।
Okay, then let's. Should
राजीव
we
सर।
get started or?
ये
राजीव
Hello,
सर,
Dr. Rajesh.
हाँ
स्टार्ट करें।
गुड
हाँ सर।
मॉर्निंग।
डॉक्टर संभवी प्लीज स्टार्ट।
यस सर।
Thank you. So I'll start sharing my screen so I can put up the presentation. Okay.
Sir, just 5 minutes. We can have a formal introduction, and maybe then you can share the screen.
Okay.
डॉक्टर
Thank
अशोक यू विल शेयर द स्क्रीन ऑफ
नो सर विल शेयर सर।
ओके ओके। तो जस्ट
Okay.
संभवी स्टार्ट
Yes, sir.
फॉर
Sir, I'm starting, sir.
ओके।
So a very good afternoon to all the respected dignitaries, esteemed speakers, faculty members, guests who have joined us from other universities, research scholars, students, and all my dear friends. With immense pride, I would like to state that University of Lucknow has now set its foot in the 100th year of spreading light through learning. With the wishes of our Honorable Professor or Honorable Vice Chancellor, Professor Alok Rai, and Dean Faculty of Science, Professor Tripta Trivedi, as a part of the centennial celebrations on this winter afternoon, I welcome you all to the special lecture series organized by Department of Statistics. The topic for today is Introduction to Statistical and Machine Learning in R. I feel privileged to extend my warm welcome to the esteemed speaker, Professor Ashok Singh from University of Nevada, Las Vegas, USA, and guest of honor, Professor Girdhar Gopal Agarwal, sir, retired professor, Department of Statistics, University of Lucknow. We also have with us Professor R.K. Singh, sir, who is also a retired professor and head and also Dean Faculty of Science from our university. So I also welcome you, sir, and all the other dignitaries. I would now like to invite Professor Rajiv Pandey, Head Department of Statistics, to welcome the dignitaries and say a few words about this program. Sir.
Okay. Thank you, Dr. Sambhavi.
Thank you.
A very good evening to our esteemed guest, Professor Ashok Singh, our respected teacher, Professor R.K. Singh, sir, chairperson of this session, Professor G.G. Agarwal, sir, other faculties, and all the participants. On behalf of the Department of Statistics, it is my pleasure to welcome you all in the special lecture on Introduction to Statistical and Machine Learning in R. This COVID-19 pandemic has taken away many job opportunities, but has given us a timely chance to put data science to good use. We are helping data science enthusiasts all over the world to put in place the necessary tools and skill sets to harness the power of data. First and foremost, as one would expect, one should get data in order. Second, deploying the appropriate tools or technologies capabilities. And lastly, training people with the right and relevant skill sets in these areas so that we do not only use the right algorithms on the right data sets with the right infrastructure, but understand what the algorithms are doing and what the results mean for decision making. This goes beyond the science of data cleaning and understanding the math behind these algorithms. It is the art of conceptualizing the output of these algorithms. Sir, we at the Department of Statistics, University of Lucknow, see these components as building blocks for any successful data science venture, building blocks that are foundational, because if any one of these components is missing or lacking, we cannot drive good data-driven insight. Let us embrace these steps with open hearts and minds and work together in our data science journey to create value at industry, corporate, private sector, and individual levels. Thank you. Happy learning to all of you, my dear participants. Over to Dr. Sambhavi.
Thank you so much, sir. Indeed, we all agree that the world is now moving towards statistical literacy, and henceforth is the need for all these topics to be discussed on platforms like this. So I would now like to invite Mr. Ashok Kumar, Department of Statistics, University of Lucknow, to introduce our esteemed speaker for this special lecture.
Thank you, Dr. Sambhavi. Talking to each other, sharing stories, and sparking conversations are a crucial part of staying connected. Now, in this pandemic period, these online lectures is one of the many ways why learning and connections can be maintained. And also, we want to make it easier to learn with the other person, even from a distance. For this, I am profusely elated to take an opportunity to introduce our today's chief guest speaker, Professor Ashok Singh, William F. Farrar College of Hotel Administration, University of Nevada, Las Vegas, USA. Sir, it is a privilege because Sir is an alumni of the Department of Statistics, University of Lucknow. He has obtained BSc from University of Lucknow in 1968 and the MSc in Statistics from the Department of Statistics, University of Lucknow in 1970. After that, he has pursued his PhD in statistics from Purdue University in USA in the 1977. He teaches the courses in advanced analytics, slot designs, statistics, and mathematical models for business. He has published more than 100 research papers in national and international reputed journals. He was also an associate editor of the UNLV Gaming Research and Review Journal. With a very small introduction, I would like to invite Professor Ashok Singh sir to enlighten us by his lecture on Introduction to Statistical and Machine Learning in R. And I also would like to invite Professor G.J. Agarwal sir, please chair the session. Thank you, sir. Sir, please.
Thank you, Ashok. Thank you, Dr. Pandey. Thank you, Dr. Mishra. So, should I share my screen or
Yes,
how
sir.
are
Yes,
you
sir.
going to? It,
No,
it
sir.
doesn't matter either way, whatever is easier for you. Just let me know.
Sir, please share your screen if it's fine with
Okay.
you.
Let me just give me 1 second. Open the presentation.
So as we can see on Sir's screen, it is 1:44 a.m. there in Las Vegas.
Yeah.
So
Yeah.
I think we must salute to the spirit that Sir has, and he agreed to deliver lecture at this time for all of our convenience. So once again, thank you so much, Sir, for agreeing to this and at this time delivering the lecture.
Well, I have to tell you this, that if it was like, I mean, I was watching cricket yesterday, so this is not a. Let me just unlock this hard drive.
Yes, sir. Sure, sir. Sure.
Just 1 second.
We also have large number of students who have joined us. So there are about 97 participants, sir, who are eagerly looking forward to listening to you.
We're missing 3 people. We need 3 more for 100.
Yes, sir, we do.
I can't. I don't know why. This thing is giving me trouble. Oh.
So we will have question answer sessions at the last of the lecture. So I would like to request all the students to please post your questions on the chat so that we can have a discussion and interaction after the lecture is over.
Okay, here. Just 1 second. Still trying to find my PowerPoint. I was just working on it a minute ago. I mean, 10 minutes ago. Let me get it from the email because I emailed it to.
No problem, sir. You can.
Oh, I'm sorry. I should have been ready. Oh,
So for all of you, for all those who are not able to join or maybe connect in Zoom, can see the live streaming on the YouTube. So this is for you, Mr. Cash. You can see the live streaming on YouTube.
Sambhavi, you may share in chat box also the link of YouTube.
Okay, sir. Sir, I'll do that.
Okay, you can see the presentation now?
Yeah,
Yes,
yeah.
sir,
Yeah,
You
we
found
can.
the
Yeah,
right
now
slide.
it's visual.
Good. Yeah, I'm sorry about this. Okay, so let's get started. Let me see if I can make it bigger.
Sir, on the top left corner, it is saying top down corner, sir. And in the down left, sir. Yes, this one. I
This
think
one?
it will.
Yeah. Okay. So I just wanted to say one thing, that both me and Gezer, we are neighbors. We have been neighbors for a very long, quite long time. And we, both of us came to Purdue in 1973. We came together, we stayed together. Then he graduated, I graduated, went to work, and he graduated and went to work in Ohio, and then returned soon after, 2 or 3 years after. But we have continued to work together since then. And it's been, he's one of my closest friends, and it's always a pleasure to work with somebody you like and respect. So with that, let me get started. So in this, I'll keep the technical stuff simple. The examples are simple. And then at the end, I'll present a couple of papers that I have done with Dr. Girdhar Agarwal. So one thing you would notice is that the terminology is pretty much similar in statistical learning and machine learning. So we both of these disciplines uh, solve or work on similar problems. It's just the approach. So as statisticians, we like to explain our solution because we're looking for reasons why something works in a certain way. The machine learning people are just trying to provide predictions mostly. Very little work has been done on explaining the results, and you will see in a little bit. So with that, let me start with a very simple example. It's a real example, so hopefully you'll find it interesting. So there was a story in, it's not that, only 8 years ago, in New York Times, that for all this time and all the work that's gone on in biology and so on, we didn't know why an alligator, what gives the alligator the bite force. We all know that the force of its bite is just tremendous. Once it holds its prey, there's no way that you can, get it to release it unless you just, kill it, like shoot it down or something. But anyway, so we did not know what made the bite so strong. So in 2012, I'm sorry, in 2012, researchers worked on this problem. So for many years, the people used to think that the crocodiles and alligators, they look different, right? They have different uh, snouts, the face, as you can see in this picture. So this is the gharial that we have in India. And this is one of the alligators. So you can see the nose is very different. The shape of the face or the nose is very different. This is thin and long, and the teeth are razor sharp. This is much, like wider. Now, so people used to think, the scientists used to think that the shapes also have something to do with it. So Greg Erickson and his team at Florida State University, they caught a total of 83 adult alligators from 23 living species. We have that many species, and if you click on it, it will take you and show you all these species. Anyway, so they rigged up a device to measure the force of its bite. They also had to make sure that when that the alligator bites with full force, so kind of like it's angry or is going after its prey. So it's not all that simple. So here is one example where one data point is, I mean, for us, it's just a data point, but for them, getting a data point is pretty dangerous, right? So here is the data. So there were 23 species, 87 alligators. So they had 2 from first species. So this is the average of the weight, and this is the average of the bite force, and so on. So this is the number of observations per species, average weight, and average bite force. So the thing is that the simple linear regression probably should not have been used, but that's what everybody has used. That's what the researchers had used. They should have used a weighted regression, but it doesn't matter. That's not the point of this lecture. So the data clearly shows that there is this, like a linear model will fit this very well. And it does, as you will see. So the way you do this in R, and most of you now are familiar with R, so I'm not going to go over all of that. But so that in this presentation, the blue lines are the R code lines, and then everything else is the output. So you can see that the intercept is 125 or 124.5, and the slope is 6.75. R square is 92%, so it's a pretty decent model. In other words, only 8% of the variation in the bite force is due to error. 92% is being explained by the straight line. So it's, in that respect, it's a very good model. Then you can, plot the data and the line. You can also plot the data and the confidence intervals along it in R, easy to do. So now, what I'm going to do is use another machine learning method on it and then compare the results. So the statistical solution, the advantage is this very simple. Here's the line. Anybody can take with a calculator, can use it to figure out the bite force of an alligator. Keep in mind that weight is easier and less dangerous to get, but bite force is a lot more involved. And that's where you can, you're taking a big risk in calculating one data point. So one more time, the statistics gives us an answer that's both predictive and explanatory. So it explains that it's telling us that for 1 pound increase in weight, the bite force goes up by 6.7 pounds. So that's the explanation of this model. Now let's look at the solution provided by either you can call it statistical learning or machine learning. At this point, it's exactly the same thing. So we'll use this tool called support vector machine. It fits a straight line. It's not fitting a straight line. It ends up fitting a straight line, depends on what type of kernel you're using. So SVM typically uses some kind of a transformation on the data, like it can use the radial basic function, or tan hyperbolic transformation, and so on, and then uses the linear method on the transformed data. But the solution is typically not least squares, is what they call epsilon regression. So you're trying to find a line that comes within a tolerance of all the data points. So in R, again, it's extremely easy to use. I mean, the form of the model is very simple. It's just like if you put LM here, it will fit the straight line. If you put SVM here, exact same model format, and you can choose a kernel. So here I'm using the radial basis function kernel. And one thing is that SVM is not part of the base package in R. So you have to download the package called E1071. I don't know how they came up with that name, but anyway. So install the package, then put it in the session memory, and then do this. So you get, if you do a summary, it doesn't print out, as you can see, the coefficients, right? In linear model, when you say summary, it gives you the coefficients. Here, it just tells you what kind of model was fitted. So this is SVM type is epsilon regression. The kernel is radial and so on. Then there are other parameters in it like cost, gamma, epsilon, that's the epsilon I mentioned earlier. And then the number of support vectors here is 17. So it's using, basically the entire model is using only 17 of the 23 points explicitly. So those are called the support vectors. So then we can also use the linear basis kernel, and you would think that it will give us a straight line. Only thing is that you have to do some work to figure that out, because again, there is no formula that is outputted. It just gives you this, then you can predict. You can predict using these models. So what you are seeing in this graph is the observed date. This is the weight, and then the observed y and observed error of 142.5 is the best model. So it beats the SVM model, whether you use the linear kernel or the radial basis function. Radial basis function is typically, typically outperforms everything else, but not in this example. So there is no theorem that says that a machine learning solution will always be better, even though if you Google, everybody will tell you that that's the case. They all think that machine learning will always outperform statistical methods. It's not true, but we don't have that name. They claim all of this. Anyway, so here we saw that the statistical solution is the best, gives the best results and it's easy. SVM radial is an algorithm where we have used the radial basis function transformation, and we don't have a formula. If you look at the SVM linear, we can figure out a formula. So this is the advantage that we as statisticians have. We can figure some of these things out, but the machine learning people, once they will just, the program will output something and they are done basically. It's up to the user to try to make sense of the results. So let's look further into these three models. So all I have done here is something extremely simple. So I don't need to explain the code. Let's go to, just waste of time. I've emailed it to you. All I've done though here is that I chose the 13 data points, basically a sequence of points. So the first point is 0, and then increment of 25. Then I predicted using the linear model, the straight line model, predicted in R using the model SVM radial, and then predicted in R using the model SVM linear. And then you can calculate the slopes, right? So it's simply this value minus that divided by the increment I had kept in constant increment. So the y2 minus y1 over 25 for each pair of points, and not each pair, each subsequent pair of points is 6.75 for the straight line, right? The least square line, as it should be. That's the slope. The radial basis function, the slope changes because it's not a straight line. It's just simply predicting it. The algorithm is predicting a value. They're not doing as good a job as the straight line. And then for the slope of SVM linear, estimated slope turns out to be 7. So it's just this minus that over 25 is 7.01. So you know that the slope is constant, so it's a straight line. So now how do we get the equation of the line? It's extremely simple, right? This is why I included 0. So that's the intercept. So bite force is intercept plus the slope times the weight. So we have a model for it. The process that you just saw, taking the results from a machine learning solution and then making it understandable, that's referred to as like white boxing a black box model to make it understandable by the user. And there is some work going on in this area now, but still a lot remains to be done because this is an extremely simple example, one predictor. But imagine trying to explain something with hundreds of predictors, right? But so there's a lot of work that we as statisticians can do in this area. I've already gone over this part, so now I'll go to another example. So in the first example, we had a continuous response with a regression problem. In the second example, it's a very famous data set in machine learning, the Titanic data set. You have all heard of the Titanic ship that sank, right? And you have also, some of you must have seen the movie. So anyway, this was the largest passenger ship at the time. It had 9 decks, a height of 175 feet. And it just, it didn't last very long. It just sank and lots of people died. So the data is available. And if you Google it, you will see history of it and also data. So here, I don't know if you can see this, but these are the columns. And here is the explanation of the variables. So P class is the passenger class, the first, second, third. Survival, whether the person, that customer, a passenger survived or not. So yes is 1 and no is 0 and so on. Name. So this is not a it's not a predictor that will be useful because, survival has nothing to do with, maybe it depends on the last name, but anyway, gender and age, and then number of siblings and spouses aboard, and then P arch is number of parents and children aboard. Ticket number is again useless, it's just for record keeping. Fare may be useful, but, and then cabin, which cabin they were put in. So some variables were useful, some are not. I picked this example because any book on machine learning will have this example. And if you Google, you will have, at least like 50, 60 sites will show up just talking about this data set. So this data set actually shows that it's really important to pre-process the data, even though it's not a huge data set. It's only had like some 1,300 data points or something. So the way we figure out the missing value is simply like there is no record of that variable for that passenger. So most of the columns, that's a mistake. This is PCL, this is passenger class. I'm sorry about that. It just search and replace did this. So there is no missing value in the passenger class, no missing value in the response, and so on. Gender, there were 263 rows. It was just not, gender wasn't there. Similarly, there is a lifeboat ID. This is just a text column, as you can see here. This is not very useful anyway. So this column I deleted from further analysis, did not use it. Most people will not use it. Gender is known to be an important predictor, and it's not a good idea to try to predict that, like missing value imputation. So I didn't do that. So then you start with your model building. Here, one thing we have to notice is that passenger class has integers in it, like 1, 2, or 3. So for the computer, it's just an integer. So if I put it in the model without telling the computer that it's actually a categorical variable. In class 1, 2, 3 is not integer 1, 2, 3. So that's the purpose of this line. And then you then delete or omit all the data points with missing values, I mean rows with missing values. You get this more, and here is the summary. So now there is no missing value. Then this is something that we don't do in statistics, but the machine learning people will always do this, and business people now will always do this. So if you have a large enough data set, if the data set is only 50 or 50, 60 observations, then you won't do that. Otherwise, you will randomly select a subset of the data and use it for training, and the remaining smaller subset will be used as a test set. So you want to build a model on one subset, larger subset, and then predict the test set, and then look at its accuracy. Okay, so this is something that we never teach in statistics, but it's not that big, it's not that complicated. So that's all that's going on here. So I'm using 25% for test set and 75% for training set. So it's just simple to do the set. You set the seed so that we can get the same result each time we run it. Otherwise, the numbers will keep changing. So this is the training set, and here is the test set, and then build a model. Then we get this model. You can see that the last column is the significance probability, and except for the last two predictors, P arch and fair, everything else is significant statistically. So that there's one thing that I want to point out is, at least when I was learning multiple linear regression, we didn't talk about multicollinearity, but it is something that I'm sure that you guys know about it, so I'm not going to dwell on it too much here. But this is a rule of thumb in statistics literature, that you calculate this variance inflation factor. In R, we can use this library called CAR and look at the values for each predictor. This is again a typo. This is passenger class. Sorry about that. All of these, if all of these are less than 5, the model does not suffer from multicollinearity. If it's above 5, then we may have serious issues. So what multicollinearity does is, if you think about it, let's say you fit a linear model. So let's say you only have two predictors, x1, x2. So you have a model y equals beta 0 plus beta 1, x1 plus beta 2, x2. Now, we know that beta 1 is the rate of change in y with respect to x1. Beta 2 is rate of change in y with respect to x2. But what we never, like no book on multiple linear regression will tell us is that we are assuming implicitly that when we change x1, x2 is staying constant. When we change x2, when we calculate the rates, when we change x2, we are able to keep x1 constant. But if you think about it, if x1 and x2 are highly correlated, like let's say correlation is 0.95, when you change one, the other will change. So basically then our model, if it has multicollinearity, is not really meaningful. It's just a predictive model. If it's high multicollinearity and you see a model, that model is really only for prediction. As a predictor is fine. As an explanatory model is useless. Because of this, because if one variable changes and it forces other variables to change, then your definition of the derivatives do not apply, right? Okay. So here is the final model by dropping the insignificant predictors, and multicollinearity again is not an issue. So now we come to the interpretation. So this is binary logistic regression. So keep in mind that log of the odds is probability over 1 minus probability of success. So if you look at the passenger class, for example, it's got 3 levels, P class 1, 2, and 3. In the model, P class 1 is missing, so that was chosen by R as the base level, right? So the coefficients are negative, and then this is even smaller. So estimated coefficients are 0 for passenger class 1, minus 1.24 for P class 2, and minus 2.43 for the third class. So that tells us that log odds are highest for class 1, lowest for class 3, which means people who had the first class tickets, they survived. The their chances of surviving were much higher than people in the third class, and which is true for, it has been true for all our lives and will remain to be true. Anyway, same for when it's like a dummy variable, sex, gender. Gender was 1, sex was 1 for female, 0 for male, and the coefficient is positive. I'm sorry, this is incorrect. Gender is 0 for female and 1 for male. So if you are, what am I saying? No, if you are a female, the odd of surviving was higher. That is well known. So this is correct. I'm sorry, I got confused. And same with age. So because it's negative, if person is older, then the chances of survival were lower. Also, if somebody had a large family, then people in that family had a smaller chance of survival. So all of that makes sense. And this, like I said, the only reason I presented it was the famous example, and every machine learning book uses it. One thing that I would like to mention is that for a problem this old, all we're trying to do is what happened back then. Machine learning methods they are used just to demonstrate their method, but they are useless. Something that happened so many years ago, all we are should be trying to do is why that happened, right? Prediction is useless because this thing is already over with, happened so many years ago. So statistics has an important role to play even in today's society. That's the thing that I wanted to point out. And here you can just showing you that you can compute the confidence intervals. You can, this error is a search and replace error continues. This is just P class. CM is just AS. I'm sorry about that. Anyway, here are the coefficients after exponentiation. So those are for the odds and not log odds. Then we compute confusion matrix. So all it is a table of observed survival.
Sir, I think we have lost connection with sir.
Yeah, it looks like.
Yes, I think so.
Sir, he might join us again, maybe.
लग रहा कुछ लाइट का इशू हुआ।
क्या हुआ कि उधर
अशोक सर,
सर आगे सर ज्वाइन कर लिया सर उनको।
अच्छा अच्छा, आई थिंक डिस्कनेक्ट
सर ज्वाइन को होस्ट सर को। सर को को होस्ट बना दीजिए।
Sir is the co-host now. Ashok sir, are you able to share your screen?
Hello, sir. You may join. You may share your screen, sir.
Hello?
Ji, sir.
Yes,
Okay,
sir.
yeah, now I see it.
Yes.
So let me try
Yes.
to share the screen again.
Okay, sir.
Yeah. I don't know what happened. Just
I think there is connection loss, sir.
now it says I'm sharing my screen, but
No, sir.
Sir,
This
we can
is
see. Sir, we can see your screen. You may please
okay.
share your presentation with us.
Okay. Let's see. Can you see it now or no?
Yeah,
yes,
yeah.
sir.
visual, sir.
Thanks. Thank you.
Please do it for on full screen, sir.
Yeah. Yeah, let me get to that point where we were going through all of this. Yeah, we were at this example. So I'm just talking about the false positives and false negatives and overall accuracy for the training set. And then we have some, we can also compute some statistical measures, and these are R-square type measures. So there are three of them that are commonly used. So if you look at a biostatistics book or a statistics book on logistic regression, you will see these McFadden R-square, Cox-Snell R-square, Nagar-Kelke R-square. So these are, even though they don't look, they're not close to one, but these are typically known to be, there is no upper limit for these. That's the one problem with these R-square type measures. So in other words, we don't know what's the maximum value of McFadden and so on. So that's why these values, even though they look far from one, are reasonable for this model. And here, yeah, so this is the predictor, the confusion matrix I was talking about, that this is 403 is the true zeros, people who died, predicted as died. And this is 217 is the number of people who were predicted survived correctly. And then off diagonal ones are the errors. So you calculate the false positives and negatives from this confusion matrix. Everything comes from the confusion matrix. So you calculate all of these. There is also, because you have covered it and also time is short and kind of rushing through it. So going through this line of code, you can get what you call the ROC curve. So the curve on the top is the receiver operating characteristics plot, and the curve on the bottom is the true and false positive rates. So here, when we did the created the confusion matrix, it was based on 0.5. That's why we have these lines. Anyway, so the area under the curve is one measure. So area under this curve is 0.78. the best area under the curve will be 1 and the worst will be 0.5. So AUC for any binary predictor will be between 0.5 and 1. So ours is kind of like in the middle, so it's reasonable. There's another statistic that uh, uh, that is computed in binary logistic regression or any binary classification problem, and that's called the Kolmogorov-Smirnov statistic. It's not the same as we use for normality tests. It's different. It's simply the maximum difference between the true and false positive rates. So is this distance? It's 0.66. Same for the test set. So these are a little bit lower than for the training set, but not that much. So you can any of these methods like SPM or random forest or XGBoost that I'll talk about just briefly will beat this logistic regression classifier. But the advantage with, again, the statistical solution is you can understand the phenomena, which is more interesting for an example like this than prediction. So some of the machine learning methods that we can use to predict survival here are SVM plus support vector machine classification. The package E1071 does that. Random forest, the method of random forest that I will explain in a minute is we use the package random forest, and XGBoost, this is the name of the package as well. So we'll now move to a few of our publications in this literature. This is the first one. This data was he collected at Girdhar can tell us more about it. I don't remember now. I think this study was done by KGMC.
Yeah, this was done by KGMC actually. This was
Do you
the
want to
data.
say something about the data, Girdhar?
Well, I don't remember right now actually. These were HIV infected patients actually. And we were trying to
Yeah,
find the risk factors for those HIV infected patients.
yeah. Okay, thanks. So here we had a total of 350 observations, and there were total of 90 variables.
Yeah, it has a lot
And
of number of variables. That was a actually
the
richness of this
complication,
data actually.
yeah. So 25 of the potential predictors had missing values, so we're not using those. And this is just a brief description of the predictors. Now I'll explain briefly the method of random forest. So all of these methods that we have mentioned, like the random forest, not the support vector, that's different. Random forest and XGBoost, they are all decision tree based. So a single decision tree works with all features of predictor at the same time. So everything goes in and the decision tree will pick one of the variables, make a split like x2 is less than something, and let's say x2 is less than 50, above 50. Then we'll pick the next predictor and choose a cutoff. So it's extremely simple method, but when you apply it, it really looks like a mess. Anyway, so both of these methods, the random forest and boosting, are based on single decision trees. So what random forest does is uses a process called bagging. Bagging is just using bootstrap plus aggregating or averaging. So the bootstrap comes in, sorry. So it randomly will pick predictors. So let's say the first tree picked predictors 11th and 15th, build a decision tree and made a prediction. So let's say y is 0. And then second tree randomly picked features 3 and 7 and and use the decision tree to make a prediction. It's y equals 1 and so on. So I'm only showing 6 of these. And then notice that except for the first and the last, all the other 4 ones are predicting a 1. So you use a voting algorithm. Whichever class gets the most vote is the prediction from the whole system. Boosting uses trees sequentially. So in the random forest, each tree, or I mean, each of these trees is independent. So the result from here is not affecting result from here and so on. But in boosting, you fit a tree, then look at the error, and then try to correct it. So it really takes some decision tree with, let's say, a success rate of just above 50%, and you put them all sequentially, and of course you're doing like thousands of these. So that's why in the end you can get a very high accuracy. Obviously, the nature of the solution is not understandable, basically incomprehensible. So the R has several boosting packages. Ada Boost is one. XGBoot is the best one so far because it uses very efficient implementation of the boosting algorithm. All of these methods use something that we were taught in minimization, right? Like the gradient method of optimization that's used in computer searches. That's what all of these methods are using. So for this data set, uh, remember that Y is binary, if HIV is present or not. So for these predictors, you can run a test of correlation with Y, and then pick the significant predictor. So that's what is being shown here, and all of these graphs are produced in R. Then use the method of random forest. The random forest has one advantage that in the end, you can print out something called variable importance. So speaking, the very first one has the highest importance, that's age, then jaundice, then TFI, and so on. All of these predictors are known to be uh, high risk factors for HIV. So with a pretty large data set, the method picked most of these predictors, and the accuracy is very high, 98%. The binary logistic regression on this data set really did not produce anything. So there are examples where prediction is our goal. Then there are other examples where, and it also tells us which features are important. It's left to us, statisticians to then take the results and try to come up with a way of figuring out how much effect age has on survival, how much effect jaundice has on survival, and so on. Not an easy task, but still a task that a statistician can work on. I don't think the machine learning people can, because they're not even thinking in those terms. They're only thinking in terms of algorithms. Here's another paper. This is an example of what machine learning people call uh, unsupervised learning. The previous ones are examples of supervised learning. All it means is that if you have a target like a response variable, then that makes it a supervised learning problem. Here it's clustering, so there is no uh, response. So anyway, this paper is going to appear in this open access biostatistics and bioinformatics. So here, this data was collected by Dr. Nirupama Agarwal and her student. She finished, right, Giza?
Yeah,
Jyoti?
she has
She
completed her
completed her
PhD.
dissertation.
Yes,
Yeah,
yeah, she just completed her PhD.
yeah. That was my impression, right? So they collected this data from Lucknow, Barabanki, Gorakhpur, Basti. It's a small fish, I believe. And they're trying to classify the fish. So I'm just going to run through it because time is almost. So this graph is explaining the predictors. So what is dorsal anchor, inner
These are
length, and
body
dorsal?
part measurements of
Yeah, body
parasites in
part.
the fish actually. These are the parasites in the fish. And these are their
Yeah.
body parts.
Hmm. Okay. So then, this part I don't really understand. All we had done here, me and Gaither, we come up with this, just the box plots by species, And you can see that some of the species, like it's very far from the rest, right? The first one, which one is the dorsal bar is very extremely high. The same for the next predictor with ventral bar and so on. So then we, I think Girdhar had chosen this method, which of course, that's the only method that we can use here because of having so many predictors. So we did the principal component analysis, and this is showing, this is the scree plot that shows percentage of variation explained versus number of components. So just the first 3 components or 2 components were enough for this problem. And you can see the plot of PCA loading. So you can figure out which predictors are important for the first component, which are important for the
Second.
so this interpretation part is the most important one, which Girdhar and Dr. Nirupama Agarwal had done. And let's see. And then the next step was to do a k-means clustering based on the principal component results, the principal component scores, and this plot of sum of squares versus number of clusters shows that after you go from 2 to 3, there is very little gain. So this is showing like a 3 cluster solution, which is what we used. And here is a plot of the 3 cluster solution. So it's able to separate out these clusters. I don't know if you can read these species falling in each cluster, but it just shows
The
that
main
it
thing
was
is that these
successful.
clusters are quite distinct actually. I think you
Yeah,
can see
yeah.
from the figure itself.
Very good separation. So it's a
Yeah,
it's a
separation is quite
successful
distinct.
application of uh, unsupervised statistical learning. There is no response variable here. Discriminant analysis, there will be a class added to it, and then you're predicting that class for new data. And this is do we have time? Can I quickly run through it?
Yes, sir.
Hello?
Yes, sir.
Okay. So this is the last thing that I wanted to present. A student here, and he wanted to come up with a model for predicting United States elections in 2020. And he collected these, the data was collected by him. He came up with the variables. So these variables are shown here. I have sent you this PowerPoint. So if you are interested, you can look at it in more detail. For me, they were just variables, right? Predictors. And then we made the predictions using 2 methods, XGBoost and multiple linear regression. So I didn't even tell you the response. So what we were predicting was the Republican percentage. Response variable is Republican percentage of total votes for the Republican candidate, Donald Trump. So if this predicted share is above 50, then that state will go to a Republican candidate. If it's less than 50, they will go to a Democratic candidate. See, the election here is a little bit different than in India. You'll see in a second. So this table has all the states. So this is Alabama, Alaska, Arizona, and so on, right? So the XGB predicted Republican share. So this is a Republican state. So it's very, very high, and the Republican candidate won easily. Same here. Arizona, which has always been a Republican state, this time the predicted vote share was higher, but Democratic candidate won Arizona. So the method made one error here, but if you count all the correct predictions, I think there were like 2 misses statewide. So what happens here in USA is that each state has what is called electoral votes. So Alabama has 9 votes, and this is proportional to the population. California has 55 electoral votes. So if the share is less than 50, this will go to Democrat. So the Democrat candidate got 55 votes basically from California. So all you do is add up all the votes for Republicans and add up all the votes for Democrats. These are called electoral college votes. And if the sum is 270 for any of the candidates, then that candidate wins. So our method was predicting Democratic candidate to win both of these methods, the multiple linear regression and also the XGBoost. And so you know, it was another successful application of the method. And it was important that we publish it before the election. So we did try and it did get published just before. Election was November 3. So otherwise it becomes useless. Everybody will say that you're just predicting the past. Anyway, that's all. That's all for this presentation. I'm really humbled by your invitation. I have such long memories of Lucknow University that I can't tell you. Me and Gaze are both. You know. My father was a professor there, and he was the dean of arts and head of the Sanskrit department. So long, long association with Lucknow University. And I also came to US because of something that happened while I was trying to do my PhD in Lucknow University. My mentor and my advisor and also friend, uh, Dr. Bhattacharya, Samir Bhattacharya, he just all of a sudden he decided to go to Australia for a while. And then both me and Gezer started to apply and ended up, we chose the same university so that at least we'd have each other's company.
Thank
Do
you,
you have
sir.
any? Thank you so much for listening to
Thank you,
this.
sir.
Thank you so much, sir, for this wonderful lecture. I am sure that participants and especially students have benefited a lot from this lecture because you've tried to cover most of the applied topics here. So we have a question from Jagriti Sahi. She's one of the students. So,
Okay.
sir, she is asking that what is SVM model?
Okay, so what is SVM model is essentially just think of it as an algorithm. So what it does is SVM model, for example, for let's say classification, like the Titanic data set. So what it will do is it will come up with a hyperplane, kind of like a multiple linear regression, except it's not the method of least squares. That's the only difference. So it will fit a plane that separates the successes from failures. It's not an equation again. It's there is no formula for the model. You just have to. It's like computer search produces that optimal solution. So what you will get is predicted values from the model. There is no formula again. And then from the predicted values, you calculate a confusion matrix, just like you do for logistic regression. And then everything else comes from the confusion matrix, the precision, recall, F1 measure, and so on. And also the area under the curve, AUC, and K statistic. Did I answer your question somewhat, Jyoti, or?
Yes, sir. Sir, I do think that she would have been satisfied with the answer. Sir, there's one more question that we have from another student, Sandy. They're saying that is there any other method apart from looking at the VIF
Yeah, here I
check
want
for
to add actually.
multicollinear? Yes, sir. Please, sir.
Actually,
Please.
Actually, VIF, this multicollinearity is just one of the problem. Actually, fitting a regression model is incomplete again unless regression diagnostic is done actually. People
That is
don't
correct.
actually, people from other branch don't have that concept actually. Just fitting a regression model is not it is incomplete unless you do the regression diagnostic. Actually,
Yes,
regression
sir.
diagnostic is the one which actually, because you see that all the regression model are actually statistical method uses the assumptions. So if those assumptions are not made, then all these things will be useless actually. Especially point estimation is all right, but if you have to do the testing of hypothesis or confidence interval, then regression diagnostic is must actually.
Yeah,
So
that's a
actually
very
now
important.
regression diagnostic is one whole branch actually. VIF is just one method actually. Now lot of other methods and all those things are available. So I just want to tell these undergraduate students especially that you should think that just fitting the regression model is not just unless it is followed by regression diagnostic. So you should start thinking from now that what is regression diagnostic, and you should go into that detail. That's my point is.
Yeah, that's absolutely right. I just wanted to add a couple of just two things. One is that this multicollinearity is a serious issue because if it's there, if there are high multicollinearities, the model itself is useless, has no meaning. But I see it in the literature, not statistics literature, but applied literature. They'll put out a model and it has, extremely high multicollinearity. So the model has no meaning, but they're treating it as a mathematical equation, which is misleading. The second thing is that in statistical learning, you can, so let's say you test for normality and it comes out extremely non-normal. So it's good to know that our model is not really, working well because the test that we have used, the t-test that we have used, they depend on normality assumption of the residual, and that failed. So what to do now? That's where statistical learning comes in, and you can use, for example, bootstrap method to compute the corrected p-values. You just use simulation to come up with new
Or you can
probabilities of.
use some non-parametric methods also actually, I think.
Yeah, in regression is, I think, meaningful. The trouble with the non-parametric methods, for example, in ANOVA, analysis of variance and so on, you are answering a different question. You're answering everything becomes in terms of medians, and sometimes
Yeah.
the so there are, it's just that it's really important for us statisticians to know these assumptions and know that when we don't, when some of these assumptions are not met, then what to do.
Sir, one
But
question I would like to ask. Uh, in multicollinearity issue, generally we have VIF is less than 5. Then
Yeah, that's the rule of thumb. Yeah.
कहते हैं. But in I was doing some analysis in artificial intelligence in using Python. They
Mm-hmm.
say that when VIF is less than 7,
Mm-hmm.
multicollinearity, why it is so such? I don't.
Yeah, yeah. These actually you will find cutoffs of like five,
The cutoff
7.
of
yeah,
5 or 7, that is
Yeah.
another problem. This is the issue of the computer programming or some statistical concepts.
No, it's the issue with the correlations among the predictors. It's not
Oh,
as simple because sometimes what can happen is one predictor is a linear function of the other predictors. So it'll be correlated with everything else. So
and
you cannot simply just calculate the correlations among predictors
yeah,
and see if the correlations are high. So that's why you have to compute the VIF, the variance inflation
e-
factor, instead of just the correlations.
okay. Sir, in SBM radial, you told me just
Mhm.
split of data for training at test sets, that is
Hmm.
75% and 25%.
That is correct.
And usually in our Indian origin, whatever
Mhm.
in that 80% for training and 20% for test.
Yeah, that's also subjective. And
That is the
probably,
subjective, not
yeah,
yeah,
it is. It is
it
not.
is
Yeah,
subjective.
exactly.
that is a totally subjective.
Yeah.
Yeah.
Thank you,
No,
sir.
the main thing is when you do the analysis, you can try with the different, for example, you can try
Yeah,
with 80, 20, 75, 25%. I mean,
yeah.
a statistician should do it actually. That is what are
Yeah, we just
the
don't do it.
difference in those
Oh,
results actually,
Ye-
because there is no hard fixed rule about similarly
Yeah,
for VIF actually.
that is just a sort of query that I want to
yeah.
clear.
Oh, I forgot to mention one thing. You remember the talk about
Particularly in
statistical
radial
electricity?
SBM.
So there, the training set is every past year, right, up to 2016, all the
Okay.
elections. Test set here was 2020, so there was no split there. So the historical data was the training set, and
Yeah.
the future was the test set.
Okay. Okay. Thank you very much, sir.
Oh, thank you, thank you.
Sir, there's one more question from our student, Suman. So, sir, since most of the topics that you've covered, as I said, so students are relating so much with all the topics, especially regression and principal components. So, there's one more question. So, she's
Yeah.
asking that in the Titanic data, if you could please interpret the gender coefficient, like the
Oh,
way
okay.
that
So
variable has been used, if you could please interpret that.
yeah. You can still see the screen, right?
Yes, sir, we can. So all
So
these have been done by our students, so they are like very easily understanding it, and then they have a lot of questions. So
of course.
That's
I'm
why we
enjoying
have
this.
selected these examples actually, so that
yes, sir.
yeah,
Yes,
Yeah.
sir.
simple example. She started with just a linear regression actually.
Yes, sir.
Yeah.
So here, so you can see that page, right? The final logistic regression model. So gender was 1 if the passenger was female, and 0 for male. So it's just a dummy column. 1 for females and 0 for males, right? So when you come to interpret, if this is positive, right, that means that for for females the survival will be higher, because for males this coefficient is 0, right? So this is positive, so the females have a higher chance of survival. If it was negative, then they would have had a lower chance of survival. So just going with the sign basically. Same for the passenger class. First class is missing, so that's the 0.
Actually,
Then
this is
second
the
class
log.
is negative coefficient.
Yeah.
Third is even more larger or smaller negative. So survival was highest for the first class, next highest for the second class, and third class had the lowest chance of survival. Did I answer your question or make it worse?
Yes, sir. No, sir. Definitely, you've cleared the doubt. I'm sure. Sir, there's one more question from Arun. He's asking, do we really need additional statistical tests to compare two ML methods?
It's a very good question. Uh, you can probably, I mean, it's not the question of need, but one could probably compare two methods statistically using Bootstrap. You know what I'm saying? So right now we will just have one accuracy, right, for each method. And we don't know which one is best because it's dependent on one test set. But if we did that, let's say 100 times and then counted which test gave higher accuracy, how many times, then you can pick the winner. So yes, I mean, I think that's a very good thought.
All right, sir. I'm not sure if we can take more questions or not. Agarwal, sir, if you could please uh, give your concluding remarks. And there's one more question that we have, sir. So I need the
Yeah, please.
permission.
Yeah.
If I can. Okay, so sir, the question says that it's from Sandeep, and he's asking, does significant regression explain the causation? And if not, is there any method to assess the causation?
That's a very good question. And this question of causation, unfortunately, cannot be answered by statistics alone.
Yeah.
Even something
Actually,
as simple as does smoking cause cigarettes, which we all know, it was not that easy to prove statistically. You have evidence that suggests. So my answer to that question is that you look at your answer, and then you have a association between y and your predictors. You're just trying to come up with an explanation. So what is more uh, plausible explanation, that's what we would go with. It's not, we're not getting a proof of that through statistics, unfortunately. That's a whole new top, it's a whole topic of discussion. There are books
See,
written on
model
this.
fitting is a model
Yeah,
fitting itself is a whole field actually. Just fitting linear regression, of course, is not enough. As I said, that
but
you should
this,
do a
but
do
this
when you
topic
will
of
do the
causation
regression
is
diagnostic.
completely,
So
yeah.
that will tell you that whether you need some more complicated model, quadratic or whatever actually. So just fitting, I mean, regression is not enough. As I said that you should do the regression diagnostic, and regression diagnostic will tell you a lot of things actually, that
Yeah, that is correct.
you have to add some more variable, or you have to use the quadratic term or what. It will tell you all those things actually.
Thank you so much, sir. Sir, I have a small question on the receiver operating characteristic curve that you were talking of, the ROC curve.
Mhm,
So,
mhm,
sir, we do have different values of sensitivity and specificity when we fit a curve.
mhm.
So, is there any, like, there are several ways which people talk of on how can we decide on the appropriate cutoff point. So, is there a proper method by which we can decide on the appropriate cutoff value for a particular sensitivity or a specificity, or it is just subjective?
It's actually not subjective. Unfortunately, very few people are thinking about that. I have no idea why. Like, I do some work with a credit company here, credit bank.
Yes, sir.
So they use all of these, right? And I have suggested so many times exactly what you are saying, that everybody just, because the computer software uses point 0.5 doesn't mean we have to use point 0.5 cutoff all the time,
Exactly. Yes, sir. Yes.
because you can change it. So what they should do is, especially for a bank, everything is in terms of money. So this credit bank is simply giving out credit card to people, people who apply for credit cards. So there is a certain risk that the bank is taking. So in the end, they make all these predictions, but in the end, they have a confusion matrix. So there is no loss for the correct decisions on the diagonal terms. But there is two types of losses, just like type 1 error and type 2 error that we talk about, right?
Yes.
So if they could tell us what is the loss of giving credit card to people who don't deserve it, and what is the loss if you do not give a card when you should have given it. They only look at the first one. They don't look at, if they don't give a card, what happens. There is a loss, but they just ignore it because nobody wants to think about it. So if we knew the losses, then we could come up with a cutoff, right? That will minimize that loss, average loss. So your question is, an excellent one, but unfortunately, the business people are.
Yeah,
I don't
that's
know
what
why.
I'm saying. I mean, there is no perfect solution. Actually, whatever is that, I mean, whenever you have to interpret the results, you have to sit down with the statistician and the stakeholder actually.
Yes, sir.
Only then some meaningful interpretation can come out actually.
But this one is
That is
not
what the
that
experience I
complicated
have
because
actually with the
everything is
doctors.
money, right? So
Yeah.
you have no loss in when you get it right, the diagonal terms, but you have two types of losses. If you could come up with a dollar figure, right, for
Yes, sir.
both,
Yes, sir.
then you just add up the losses for point 0.5, point 0.4 cutoff, point 0.6 cutoff, and so on, and find the cutoff that gives you the smallest loss.
Yes.
Not that complicated, but I don't know what.
Yeah, because most of the people, they always have this conception that it's subjective, and if it's point 0.5, so it has to
It's
stop there.
not. We have
But
made
yeah,
it subjective. It's
yeah.
just like, when we do testing hypotheses, we simply ignore the type 2 error,
Yes, sir.
right? It's the same thing, same concept.
Yes. Thank you so much, sir. And I now request Professor Agarwal, sir, to please give his concluding remarks, sir.
Yes, yes.
Um,
Yes, I actually, I should again thank Dr. Singh about delivering the lecture at such an odd hour. Of course, he is humble enough to say that he has no problem, but still you should thank him for that.
yes.
And actually, I keep learning because I'm here, so we were together for a long time. I mean, here in Lucknow also, and we were not only collaborating in the academic, but we were collaborating in the games also. He's a very great sports person also. So I have learned a lot of sports and all those. So overall, and actually in the software also, he keeps me updated. Uh, I till now I continuously, so that benefits me a lot. Anyway, I am what I want to say is that I am a great proponent of this program R. The main reason is that I mean most of people here are using the pirated version, which is not the right thing to do. So if you start using the R from now, especially for example, I remember I have a problem. I sent a paper in some journal outside. So they specifically ask about the version and the license about the software you use. So you have the problem at that time. So if you use R from the beginning, at least you will not have that kind of problem actually. So in that sense, you should start using the R from now because it is free and there will be no problem. And I mean, when the daily people are adding the latest software, you can add your own software to this and all those things. Everybody knows that. So R is a good program, and as far as machine language is concerned, of course, this is a good concept. But as Dr. Singh also, and I also think that because it is mostly based on the algorithm, the main problem comes in the interpretation. The results which you get from the machine language, it will be difficult to interpret, whereas the results which we get
हम
statistically
देखा था
from
उस दुकान में दिखाई था
regression, so you can easily interpret those results.
आपके
So
सीनियर साहब
So this is, and the main thing and the other thing which I want to advise the students is that you should start using and start from a simple example and then progress it to more complicated analysis. And the main thing is that the message which I always convey is that you should stick to your statistical method and you should not get away by the pupil from other fields. We want that you should get these results. You should try to use statistically rightly, not badly. That's all.
I agree with you, Girdhar, 100%. I just would still
No,
like
this
to
is the
add,
which experience I have from the medical people.
yeah,
They just, I mean, they will come, they will not consult from the beginning. They will come with their data and do this thing. I said, how can I, when though the results which you have collected data are not, matlab, not having those assumptions, so how can I apply the statistics?
That's very
yeah,
true.
that's a challenge in itself. But my advice to all students is really that learn what you're learning, learn your statistics well, but don't forget that there are other, other terminologies even. Because machine learning people are doing exactly the same thing, they're solving the same problems. It's not difficult for you to pick up what they are doing. It's really not, because I'll tell you one thing, 99% of the usage of machine learning methods is without understanding. They just understand the tool. You know, very few people will know the real math behind it. You as statisticians can learn a lot more about it than the machine learning student, students coming out of computer science and data science and so on. You will have the edge because you understand the tools. They don't understand the tools. They just understand the algorithms. But you can't just say that we are better and we won't worry about the machine learning because they are the ones getting the jobs, right? So you have to keep current with what's going on. Um, statistics is being pulled in that direction. I'm not saying get pulled, but I'm saying keep aware of what's going on so you can also contribute. I mean, I see in this like the Credit One Bank, there's so many students. I mean, not students. I'm sorry, workers from India and China and all, because they can't fill the needs. They have some of them will just take like a certification class for a month. But if a statistician take that class, then he or she has a much better understanding of these problems and the solutions than someone coming out of a just a computer science background. I've seen so many mistakes being made by researchers in machine learning methods because they have no idea, of the real problems. That's all I have to say.
Thank you so much, sir. Rajiv Pandey, sir, should we conclude?
Yeah, thank you, Professor Singh sir, and respected Agarwal sir for nice advice and for dedicated for our students, and also request Ashok sir to, I think, honor जो क्या कहते हैं Professor Singh, and conclude the session. Thank you very much, sir.
Thank you, and I'll be willing. I mean, हम जब भी आपको अगर कोई क्लास पढ़वानी है, I'm willing to teach that. No problem.
Okay. We will be in touch with you, sir.
Sir, I want to say something.
And yeah, Ashok, please.
Sir, nowadays, due to this pandemic, this technology is very regular. But I have remembered that in 2018, sir delivered the first lecture from the USA that we have conducted in our conference hall. So that lecture were very, you can say, we were very enthusiastic to learn to see how a person can deliver the talk, how can we learn. And I shared a few clips on the Facebook after sir your lecture that were also appreciated by the so many persons from the other universities also. A very nice initiative that you have taken. But now this is the new normal, so we can organize these kind of lectures on the very regular basis, so our students can learn, can have the idea about the latest technology as well as the latest updation, the latest coming technologies of the statistics also. So thank you so much, sir, for taking
You
this
have no
time to deliver the lecture.
idea.
As all of us know that it's a 3:30 around times in the morning time of at your place. So really a very thank you, sir. Thank you.
Don't thank me for that part. I'm telling you, I've watched every single cricket match so far. India,
Sir, that's so sweet of you.
well, the first two ODIs were not so sweet. You
Yes,
stay
sir.
up all night, you lose this.
Okay, somebody. You
Yes,
may.
sir.
So,
Okay.
So
thank
Thank
you.
I
you.
express my gratitude to the Honorable Vice Chancellor, sir, Professor Alok Kumar Rai, sir, for always encouraging and supporting us in all our ventures. My gratitude towards Dean Faculty of Science, Professor Tripta Trivedi, ma'am. And we are also grateful to you, Ashok Singh, sir, for accepting our invitation and sharing all your ideas with us. I am sure that the students have benefited a lot from this lecture. We look forward to more such lectures with you. My gratitude towards Professor Gigi Agarwal sir and Professor R.K. Singh sir for joining us today and sharing their ideas. Thanks are also due to the head of the department, Professor Rajiv Pandey sir, for organizing this special centennial lecture series. I express my gratitude to all the faculty members of the department, especially Mr. Ashok Kumar, to the research scholars, and to the students of the department for their active participation and making this lecture series a successful one. As I said that this is just the starting, we will be continuing with these lecture series in near future as well. So stay updated and please take care of yourselves. See you on the other side. Thank you so much.
Thank you.
Thank you so much, Dr. Mishra.
Thank you.
Okay, hope to see you all.
Thank you, sir.
Thank you, sir. Thank you.
Thank you so much. Thank you so much, Dr. Pandey. Thank you so much,
Thank you.
Ashok.
Thank
Bye,
you.
गिरधर.
Yeah. Bye.
जहाँ सोने की कोशिश करें.
Okay, sir.
Okay, sir. Thank you.
Okay, thank you.
Okay, thanks.